So if you think of angular frequency as the number of waves that are produced in 2 pi seconds, or 2 pi, whatever units used for time. K would be the number of waves produced in, if we're dealing with SI units, the number of waves produced in 1 meter. Taking what we've talked about already and just sort of presenting it. We already talked about the period is going to be 2 pi divided by the coefficient of the time variable, so 2 pi over omega. And then the wavelength is going to be 2 pi divided by the coefficient of your x value. Questions up to here? And I'm about to do an awkward transition here. Considering there's a testimony, are there any questions concerning that?
Concerning what?
The testimony. Okay, like I said, you need to make an awkward transition. All right, so back to this. All right, so now I've got this idea of period and wavelength. Let's flash back again to 151, chapter 2. What is the formula for speed?
Distance over time?
Yeah. And the distance that a wave travels is, if I think about one cycle, the distance it travels is just the wavelength, and the time it takes is just the period. Now, in 151, we then took it and said that's the wavelength times 1 over the period, which is the wavelength times the frequency. That was 151. We're not going that path, just hopefully bringing back some memory. From here, I know my wavelength is going to be 2 pi divided by k. My period is 2 pi divided by omega, and we end up with omega over k. So I can figure out the speed of the wave just by taking the coefficient of time and dividing it by the coefficient of position, and I got my wave speed.
What letter is that?
The omega,
The funky looking one. For
the one that was kind of like a W, or you said funky. Oh, this one right here?
Yes.
Lambda.
Lambda.
Using the typical physics approach of length begins with L. What Greek letter starts with L? Oh, lambda. It doesn't explain why omega for angular frequency, but. All right, so we've got speed of a wave. Any questions up to here?
No.
So let's take a look at an electric, and also an electric field. Here's my electric field. We got some central axis here. That's my electric field. That would be E sub m. And this is just a snapshot. It is, the wave is moving, so, but we don't need to look at a snapshot. Now the magnetic field is oscillating along with it. So the magnetic field, and this is just going to be dazzled by my ability to draw in 3 dimensions here. I'm assuming you will draw to your own level of perfection. All right, so first I'm just gonna do it in the air, and then I'm gonna show you what it looks like when I try to draw it.
Mm-hmm.
All right, so we're starting here. The magnetic field is gonna be coming out, in, on the other side of the board, then coming out, in, outside of the board, out, in, and so forth. It's gonna oscillate along with it. It's gonna have the same angular frequency, the same wave number as the electric field. So now how do I draw out and in? That way. All right. All right, that's my attempt. The red line is coming out towards you and away from you. The yellow line is going up and down. If I had to draw, I mean, it is a vector. If I have to draw my magnetic field lines, this is G. Sort of like that. And my electric field lines, and so on. So I have these two sets of electric fields that are going basically vertically and in and out. Questions to hear? Because I'm pretty sure I know what you're thinking. Hey, this is great, but can we connect it to Maxwell's equation? Yes. Yes, we can.
Oh, thank goodness.
Let's bring in two major Maxwell's equations here. We have the sum of the electric field dot delta L is equal to negative delta phi sub B over delta T. And we have the sum around a loop of P dot delta L is equal to mu naught I enclosed plus mu naught epsilon sub naught change in the electric flux over change in time. First one is Faraday-Lentz's law, and the second one is Ampere-Maxwell's law. This is Faraday-Lentz, and this is Ampere-Maxwell. Or Ampere's law with Maxwell's correction. On the left-hand side of both equations, we have, in calculus, it would be called a line integral. We're not going to do a line integral. Well, not as such. Basically, I need some loop that I'm going to take my electric field around, or some loop I'm going to take my magnetic field around. So what I am going to do is I am going to create my loop. It's like a Gaussian surface, except it's an Amperian loop. It is a make-believe loop that we will exploit. And put down it somewhere, there it is. So I'm going to create a loop right there, of height h, and of distance here, delta x. So go ahead and bring that up again. So I have a width of delta x, a height of h. My electric field, where I've chosen it, and I can choose it anywhere, but I've chosen it in the convenient spot. My electric field is going up at that position, and so I have some electric field here. And over here I have, well, the direction's already set, that's going in that direction, so so I have an electric field there, and here I have an electric field plus some change in the electric field. Now, at this location, when my electric field is going up, my magnetic field is coming out of the board. And so if I threw my magnetic field, well, my magnetic field is coming out of the board. Now, we're going to do a loop, and the question is, in which direction do we take the loop? Well, you take the loop, you start at some location, and you work your way around, right-hand rule. You start here, because I want my magnetic field's coming out, I am going to do the loop in that direction. So, I'm going to label this lowercase a, b, c, and d. And so, looking at Faraday-Litz's law, I have my electric field along A dot the change in length along A plus the electric field along B dot delta L B plus the electric field along C plus delta L C plus the, that's not a plus there, that should be a dot there. The electric field along D dot delta L D. That sum, that's the left-hand side, is going to be equal to the negative change in the magnetic flux with respect to time. And the magnetic flux is just my magnetic field times that area. So that's going to be the negative change in the magnetic field times the area, which is the negative, well, my area is not changing because I set it. I set my area to be that. So that's negative area times the change in B over time. So all I have to do is solve this. I will come out with an equation for omega over K. I know that will be the speed. However, that will have to remain until Thursday. A cliffhanger. It really is amazing how it all works out. You might not be as excited as I am by it, but it is still pretty darn cool.
I'm always excited.
Well, yeah.